All right. So how was the lab? How was the first lab? Any thoughts? Is it good?
Yeah, I thought it was good. It was cool to actually get to use the 3D printers.
Good, good. Yeah. So I think for some of you, that's the first touch of a real 3D printer, right?
Yeah, it was pretty cool.
All right. Yeah, I think you guys will have a lot of chance to even mess with these 3D printers because for the final project, you have to prototype your design using the 3D printer. Another thing will be the software. I have contact the sales department of Autodesk. They used to have very good online courses, free courses for us, and for the previous year, but I haven't heard back from the Autodesk people. So I don't think that will be an issue because they want you guys use Autodesk software, Fusion 360. So I will let you know once I got the available enrollment for you guys. Basically, you just need to get yourself a registry on the Autodesk website and get enrolled in their class. If you haven't used Fusion 360 previously, you could follow the class and get to know how to use it. Basically, the design of the project will be, I mean, the design of the 3D shape you will prototype in your project will be done in the Fusion 360 software. So if you have any questions regarding this, just let me know. Any concerns or, all right? Okay, let me share the screen and continue the lecture. Also, you will have the first homework after this lecture. So basically, we will talk about some computation aspects of the field stabilization modeling, and you will have a chance to do a little practice in homework. All right? I will release the homework afterwards, after this lecture. So, I think I have made something wrong. Let me redo it. Okay, there we go. So in last lecture, we talked about some of the processing, including those surface smoothening methods. For example, if once you complete your printing, the surface of the object could be quite rough, like the one shown here, right? So you could have multiple ways to smooth the surface, such as some sanding, right? Or you could use some chemistry-based method like the vapor smoothing, specifically for the ABS plastic. You can easily use some solvents to smooth out those rough features and have a very smooth surface afterwards. But for the PLA we use in our lab, basically it doesn't work. So you have to use other ways to smooth it out. Probably you want to use the sanding, right? And it's specifically for the ABS or other thermoplastic. Besides the smoothing, we could also have some color printing. There's some new development like this DaVinci color 3D printer. So basically, you could print a colorful object instead of just a single color object. And basically it will print the CMYK inks into a white PLA material to produce the color parts. And let's look at a video about this. Let me try to play the video, and I will open the
When
captions.
color broadcasting aired in the 50s, people were blown away by the magic of a full-colored image. And just like with television, the desktop 3D printing industry has been stuck in black and white, but XYZ Printing aims to change that. We bring you the DaVinci Color, the world's first full-color FFF 3D printer, and thus ushering in the new full-color era of desktop 3D printing. Powered by 3D ColorJet technology, the DaVinci Color combines inkjet printing with fused filament fabrication to create full-color prints. CMYK inkjet cartridges drop color onto every layer of PLA filament and are easy to maintain since they can be removed individually. With a hands-free auto-calibration system, motors move the knobs for you so you don't have to worry about calibration. The DaVinci Color also has a robust 7.9 by 7.9 by 5.9 inch build size, and its easy removable print bed allows for easy print extraction. The 5-inch full-color LCD touchscreen interface enables you to navigate through all printer functions. And with Wi-Fi and USB connectivity, sharing designs with your printer has never been easier. Let the DaVinci Color take your design to a new level, allowing creative minds like animators to produce prototypes in true color that are ready to be shown to executives and producers. Character designers to print out their favorite comic book, video games, or fantasy characters in their authentic shape and in full color. Or art designers to give their clients a glimpse of the final product by printing out scaled-down models of their artwork. Bring your creations to life in full color with the DaVinci Color, the world's first full-color fused filament fabrication 3D printer.
Okay. So as you can see here, it's not just a single color could be print using the fused deposition modeling printers. It can also print those multiple color objects. Also, there are other new technologies such as this mosaic palette. Basically, it will accept 4 different filaments in 4 different colors and merge them to a single filament. As you can see here, this is the input, right? So there are 4 filament input, and this device will merge these 4 filaments together to have a single filament for the printing. So in that sense, it's like an accessory of a normal 3D printer, meaning you can purchase this and add this onto your existing 3D printer, and then you could have the capacity to print a multicolor object. I think this is no, it's not a video. And that's also another solution for the fused deposition modeling process with a capacity of multi-color printing or multi-material printing. Another advancement in recent years is this BAM process, big area additive manufacturing. As you can see here, these figures actually are from the Oak Ridge National Laboratory, laboratory, I mean. So they have a very large 3D printer. You can think of it's the scaling up version of those desktop 3D printer fused deposition 3D printer. It's a room level. So as you can see here, it can print really large object like the car showing here. Basically, the appearance of the car is printed using this BAM process, and also some of the even house showing here. They have a whole room for housing these printed objects. For this one, for the house, basically it's outside of their laboratory. And I was there when I was teaching at Tennessee Tech. So we have a joint program with Oak Ridge National Lab. I used to teach there during the summer. So I got the chance to visit their facility. So it's a gigantic 3D printer compared to what we have in the lab. And so this is, as I mentioned, invented by the Onanel. And they used injection molding pellets rather than the filaments. Because as I mentioned, the pellets is more, it's cheaper compared to the filaments. Basically, you can use the existing material for injection molding instead of some special treatment to convert it to filament. So you save this process, therefore you save the cost. On the other hand, there are more material available for the pellet instead of the filament, right? So as you can see here, the area for this printer is big. So it's almost impossible to build up a heat chamber, right? And they utilize the carbon fiber filled plastic, meaning for them, they have the carbon fiber mixed with the thermoplastic and during the printing. So can you think of what is the reason to have such a carbon fiber? Anyone can give me an answer?
It probably gives it some like stronger properties. Reduces maybe.
What was that?
Reduces defects, maybe.
Yeah, it's close. It's close. Any other thoughts?
Would it reduce the warping as it cools down?
Yes, you got the right answer. So as I mentioned, during the FDM process, the biggest thing is this warping, right? Due to its thermal process, the shrinkage of the thermoplastic, it has different ratio among different layers. Therefore, they have a chamber for many process. For many printers, but in this case, there's no such a chamber. It's not possible. Just to think about how big it is, right? It's not realistic to build a chamber. On the other hand, if you think of some other real applications, like if you build up something which is even bigger, or on another planet, there are some projects they are targeting to build the rehabilitated housing at different planets like Mars, right? So it's not possible to build up a chamber there. So that's not desirable. In that case, you have to figure out a way to compensate this warping or curling during the printing due to this thermal effect. So the solution for this BAM is they combine the carbon fiber into the thermoplastic material. Because carbon fiber has a better thermal shrinkage have a better material properties. In that case, this carbon fiber will reduce this shrinkage and compensate the shrinkage, and turns out ultimately it compensates this warping or curling. So that's why they have this carbon fiber field in the plastic. We have a similar machine in the Brinkmann lab, and I don't know you have the chance to take a look at it. So that is a machine from the Titan Robotics. So we also use the carbon fiber during the printing. Although our machine is not as big as the one at Oak Ridge National Laboratory, but still, it prints objects much bigger than the desktop one. So therefore, we also have the carbon fiber filled plastic printing. Also, it consumes plastic pellets instead of filament. So if you have a chance, you could definitely take a look at it. Also, as we mentioned, the filament and the pellets, right? Basically, the pellets has a much lower cost than the filament. Also, there are a lot more material available in the form of pellet instead of filament. So that's why it's more desired to have a pellet as the input material during this printing process. And let's take a look at this video. I think there's no caption for this, but this machine is called the Atlas, also from Titan Robotics, similar as the one we have in the lab. That's the bigger fused deposition modeling machine consuming pellets, right? Also, we have some multi-nozzle printing capability. So the concept is, well, instead of only having one printing head, we could have multiple ones to print the different part of a big object. And basically, you are building a part in parallel. That definitely saves time and improve the production rate. So we have, so Autodesk project Aster is one of the example for the multi-nozzle printing. As you can see here, there are multiple nozzles working on the same part. Of course, you need to carefully divide the tasks for each of the nozzle. And also you want to avoid the collision of the nozzle, and also due to some parts could be, so you want to imagine where there will be collisions. First of all, you don't want to have collisions between different nozzles. That's one one possible for the collision. Another thing is, if you build one part first, and then you build another part, you build one region first, and then you build another region, use a different nozzle, that could be collisions. So I can draw a little illustration here. For example, you have some object like this, right? For example, you build, let me see, let's see, you build this part first, all right? You build this part first, and then you want to build this part. When nozzle move to this region, because you already have this printed, that could be collision between the nozzle and this wall. So definitely you want to plan your motion to make sure when this region to be printed, there's nothing block. So it is related to very complex planning of the tool path. So as you can see here, the multiple nozzle brings new opportunities, higher production rate, more flexibility in the geometry. On the other hand, it brings difficulty in the planning, avoid of collision, and so on and so forth. Always trade-off. But I would say the prone is bigger than the cones, right? So that's why this kind of processing is catching attention from both the research and also the academia and the industry. All right. Any questions so far?
So I was wondering,
Yeah.
since it's so cost effective and there's such a large variety of pellet material, why are we even still using the filament method for 3D printing?
Oh, that's a good question. First of all, for the filament, it's easier to utilize. It's, if you, I will show you the working principles for the fuse deposition modeling, especially the feeding mechanisms. And also we will do some little computation afterwards, after this slides. So in one word, it's easier to build such a machine utilizing filament, but it's not cost effective to use filament compared to pallet. So that's why it's the most of these consumer level printers utilize the filament. Also the process and the mechanism to convert pellets into those plastic flow would be more difficult for those desktop machines. It consumes higher energy as well, which make it essentially not quite available for the consumer level. Just to think about, you definitely don't want a young kid to get burned utilizing a pallet-based printer. So it's safer. It's the design and the hardware is simpler to utilizing filament. That's the reason. Any other questions? No? Good. Okay, let me stop sharing and open another slides. Just 1 second. So we talk about the basics of the fuse deposition modeling, and let's go to some more details, especially the computation of the fuse deposition modeling. So the goal is to let you guys understand why these the parameters are set like this. I think you have played with the software associated with the Prusa machine, right? So then you might ask why there are parameters like these, why we should care about these. basically, I hope this lecture, the lecture 3, will answer some of your questions. Let me share the screen. So if we simplify the fitting mechanisms for the fuse deposition modeling, basically you can consider it like this. There are two neural wheels pinch the filament and pull it into the heated nozzle. Basically, if the two wheel rotate in this way, this filament will be pulled and moved along this direction. And in contrast, if you revert the rotation of the two wheel, it turns out this filament will be pulled off from the printer, from the printing head, right? Then you will immediately think about the speed, right? Because we have such a rotation of the neural wheels, and how this speed of this rotation will change, will affect the extruded plastic, and that will also be related to some settings, right? Some printing settings, and let's find the relationship between them. So if so first of all, if we know this neural wheel turns with a given rotation per minute, so what will be the linear speed? And basically the linear speed is the extruded plastic exits the nozzle. So in one word, this is the filament, right? And the filament will be fitted to this printing head. And after the filament is heated and melt, it will be pushed through this end hole of the hot end. And turns out this material will be placed on the platform, building platform. So you want to basically here is here we want to compute the linear speed that the material is placed onto this platform. So that's the question set up here. Also, another thing you want to know is the speed with which you move the nozzle over the building platform must be reasonably close to this speed. So that means when this material is pushed through the hole, and at the same time there will be a motion to move this nozzle, and such that the material will be placed onto the platform like a line, right? And this motion of the whole printing head should be compatible with the speed of the material exits the nozzle. So these two should be similar. And when you play with the software, right, there's one option that is the printing speed. And basically, if you change this motion of the nozzle, you actually also change this, because they are associated with each other. So that's why it is so important. So any questions so far about this speed, linear speed? Nope. All right. But what we talk about here actually is based on one assumption. That is, there's no slippage between this neural wheels and the filament. So that means always the motion of this filament is same as the tangential speed of the neural wheels at this point. So that's the assumption. If there's a slippage happens, then this assumption does not stand. So that is the thing you want to keep in mind. And that is why if there's a slippage happens, usually your printing will be messed up. You will have a really bad prints. So keep in mind to avoid slippage. It will make this printing fundamentally doesn't work. All right, that's the setup of the question and assumptions. Then we want to kind of solve this question step by step. So as I mentioned, the speed of this filament, I mean the linear speed of this filament moving towards this direction is the same thing of the linear speed at this tangential point on the neural wheel, right? So then we first compute this tangential linear speed. Then what we need to know, first, we want to know the diameter of the neural wheel. We use the dk to represent the neural wheel diameter, as we can see here, right? So we have the dk and we have pi. So it turns out this will be this the whole length on this circle, right? And then we have the rotation per minute. By multiplying these two together, we will have how much distance it travels for this wheel in 1 minute. And it turns out it is the linear speed at this point in 1 minute. But usually for the speed, we want to have a unit to be millimeter per second. Then we multiply this to convert the unit. And turns out this is the final result. The tangential speed of the neural wheel at this point in the unit millimeters per second. So any question for here? No? Okay, that's clear, right? Now we know the speed of the the tangential speed here for the neural wheels. In another word, we know the speed of this filament travels, the linear speed of this filament travels in this direction, right? Now we come to compute the speed for this. So as you can see here, the diameter of this filament, sorry, and this output trace is different. The diameter here and here, they're different. So we need to do a little conversion here. The only thing we know is, well, the the inside material volume should be same as the outside material volumes. So they are invariant to each other. So then again, we convert this question to, how about we first compute what will be the input volume of material. Or we could compute the volumetric flow rate. That is what is the volumes of the material into this nozzle per second, right? That's what we want to know, because this will lead the result of this. Okay, then let's look at it. So how we compute? Basically, this can be considered, this filament can be considered as a cylinder, and the cylinder has a area and a linear speed. So the area could be computed using the filament diameter here, and also the speed, right? We have already come up with the speed in the last step, right? That just to keep in mind, it's a little confusing. I want you to focus, right? It's a step-by-step process. We have this linear speed, and we have the area here, and multiply them together, it gives you the volumetric flow rate of the input material. And basically, you just do little computation, and you got this, which is the input volumetric flow rate. And remember, how much inside here, pushed in here, will be the same as how much you got pushed out here. So with this invariant, we are able to compute this linear speed by make them make the two be equivalent to each other, right? So this flow in, we have come up with the value. And for this flow out, so as you can see here, this flow out is relevant to the diameter of the nozzle over here. And also, it is related to the linear velocity of the the linear velocity of the material over here, right? So this is this is what we are looking for, the linear speed of the material outside of the nozzle. And this is what we know, because this dn is the diameter of the nozzle, and pi squared of dn over 2 is the cross section of this area, and this is the speed. So by multiplying them two together, it gives you the volumetric flow rate for the outside, for the output material, right? And as we know, this output material flow rate is same as the input flow rate. So by put them together, the only unknown is this V out. Therefore, we have come up with the volumetric, the linear speed of the material outside, go out of the nozzle. It's a little complicated. So any questions so far? We can go over again if you have anything you don't understand.
I have a question.
Sure.
So you're just saying basically divide the left-hand side by the first section of the right-hand side of the equation in order to get the linear volume?
Exact. Linear speed is this is not a volume, it's a speed. Because just keep in mind, our goal is to find out the linear speed of this flow out of the nozzle, and that is what we can control in the software. So find this link. Keep this in mind. All right.
Okay.
Mm-hmm. And what you described are correct. Basically, you just divide this part by this. I mean, divide this part by this, and then you have the linear velocity. Any other questions? So there will be a assignment problems related to this. So I just want you to fully understand it. All right. Also, it is possible to know the volumetric flow rate out of the nozzle. Actually, as I mentioned, this volume flow rate out of nozzle is same as the motion of the whole, the linear motion of the whole hot end. So, and that is what you can control in the software. So if you gave this speed, that means you've already determined this volumetric flow rate. That means this is already known. And also this cross-section area of the nozzle is fixed. I mean, with the same nozzle, it is fixed. And you could decide what will be the volumetric flow rate for the input material. So same equation, but with different known and unknowns. So in this case, this is known. It's a little messy. Let me clean up. So in this case, if you've already know this, and actually this could be the user input. If you know this, and this is fixed, then you could come up with this. And it turns out you could change this, because you could determine what will be this a rotation per minute. And it turns out this 3D printer, the neural wheels will, I mean, the rotation of the neural wheels will be changed according to this input. And that's how you control the printer's motion. That's why you can set it up in the software. So that is actually the usual way to utilize this equation. Basically, you set up this, and that will modify this rotate per minute of the neural wheel accordingly. All right. So be sure to understand this equation and know what will be the variations. If there are different questions, different knowns, different unknowns, you should be able to solve it. So keep this in mind. All right. So any questions? Okay. I think we can have a 10 minutes break. Let's go back in like 11:05. All right. All right, let's go back. Let me share. So we just described how to compute the linear speed of the material flowing out the nozzle, right? And let's look at how important it is. So if you have a too fast or too slow speed for this nozzle, what could happen? Here shows you some example. If the material moves too, if the nozzle or the printing head moves too slow, you will have this excess material printed. And it turns out it will make the accuracy of the printing really low. Also, sometimes if the material is extruded too much at one time, it could block the motion of the nozzle as well, because the distance between the nozzle to the platform is very small, and that could make the whole printing fail, right? In contrast, if the nozzle moves too fast, well, that could be some cases like this. There will be some void or gap produced during the process. That is, before enough material is placed onto this platform, the nozzle has been moved to another position, and there will be less material printed in that case. So that is very important if you set up a proper nozzle speed. And if there's something wrong there, you want to make adjustment, and that will make your printing have more chance to get success. All right, that's the motion of the nozzle. As I mentioned, the motion of the nozzle should be compatible with the flow, the linear speed of the plastic flows out of the nozzle, right? These two should be associated. So another very important setup or concept for this fused deposition modeling is this heat-related equation here. As you can see, there are multiple things over here, and it's a little hard to understand it as a whole. Instead, we can kind of dissect this whole equation into different portions and understand them one by one. So first of all, this H is the total energy consumed to raise the temperature of the material. And that's the target, right? And on the right-hand side, we have multiple parts. First of all, this rho V represents the mass. Rho multiplied by V is the total mass of the material to be heated. And the rho is the material density of the material. The material density in the gram per cubic centimeter. And a V is the part volumes, also in the cubic centimeter. And then in the bracket, we have three portions. The first one is the heat density up to the melting point. And to compute this heat density, we have to know this heat capacity of the solid and the liquid. This in this case is solid, because during the process, actually there is a phase transition. the filament first is in solid state, and then it will be melted and be converted to a liquid state. Therefore, we have two distinct heat capacity in this process. CS is the heat capacity for the material in the solid state, and CL is the heat capacity of the material in the liquid state. We need to compute them separately, right? In that case, we have this heat density computed using this heat capacity and the temperature change, where the Tm is this melting temperature and TO is this starting temperature. So basically, if we look at this process, let me draw a figure to illustrate, I mean the chart, graph to illustrate it. All right, if we use the horizontal axis to represent the time, right? And use this vertical one to represent this temperature. So at the very beginning, we have the material is in the room temperature, and then we heat up to this melt point. And then from the melt point to its printing temperature, there's also requires a little time, and afterwards it becomes, no, I think that the drawing has something wrong. Let me erase it. It should have different slope, like this, and finally it becomes a straight line. So at this point, that's the melting point, Tm. And at this point, that's the room temperature. And at this point, it is printing temperature. So between here and here, the material is in the semi-liquid and semi-solid state. And no, I made a mistake. It should be in the solid state. From T0 to Tm, it is a solid material. And afterwards, it becomes semi-solid, semi-liquid from Tm to Tp. And afterwards, the material is in liquid state. So that's why we want to have the two different portion of to compute the heat density, because they have different heat capacity. Basically, that is how you compute this for from here to here, right? And then you want to have this the other portion, that is the from the melting point to this printing temperature. And also you want to utilize this liquid heat capacity. And there's another part, which is the HF, that is the heat of fusion. So besides besides the energy consumed to melt the material, also there are some consumed in the heat fusions. So you want to consider about that as well during the process. So basically, you combine these three together and multiplied by the total mass, and it turns out you will have the total energy consumed during this process. Okay. Any question about this equation? Nope. All right. let's look at some example. So if we ignore the loss of heat from the conduction, convection, and radiation, then how many watts are needed to heat up the 1.75 millimeter diameter PLA filament? If you are printing at a 15 millisecond with a 0.5 millimeter diameter nozzle, right? Basically, that is you want to utilize what you have learned, of course, this equation, to come up with a solution. Let's look at, I will show you how to compute it. Please pay your attention to what I solve, how I solve these problems. And again, there will be a similar question in your homework, and you want to fully understand it. All right, so the question is asking you the watts, right? That is the joule per second. But what we have in this equation is just a joule, right? The energy. So that means you want to divide the second, divide the time for both sides of the equation. And then what you have will be this watts, right? But first of all, you want to deal with the units. So basically, there could be different unit systems, especially when you're talking about some manuals or material guidance for the printer, which you obtained from the internet. It could have quite inconsistent unit systems. And in that case, definitely you want to do a unit conversion first to make sure you will have the correct answer. For example, this material density is in the gram per cubic centimeter. But sometimes for this heat capacity of the solid material, you have the joule per gram per Kelvin, right? So here, the temperature is not in Celsius anymore, it's in Kelvin. And for the Kelvin, it has this relationship. Basically, it shifts the temperature in Celsius by 273, right? So that's the way you convert a temperature from Celsius to Kelvin. But the good thing is, you don't actually need to worry about this much during the computation. Why? Because here and here, basically you care about the difference between two set of temperatures. In that case, this will be canceled out, right? And it doesn't matter you use Kelvin or Celsius. It turns out this will be canceled because you have this subtraction. So even you have the Celsius temperature, by substituting them here, you will have the right answer because you are finding the difference between the two, and Kelvin is just a shifting of the Celsius temperature. So it won't make change to this difference. So that's a good thing. But for other units, you might need to be careful. For example, in this heat capacity of the solid material, there's a gram. But for the heat capacity of the liquid material is a mole here, right? Mole is usually used to represent the mass of the liquid materials. And for here, well, you definitely want to convert them using this relationship, these equations, right? Basically, you just multiply this and it will convert the mole to gram, right? Also, this density, material density could give you a little trouble. For example, there are some cases this is not a cubic centimeter. It could be a cubic millimeter, right? Then make sure you convert this to this, right? But the point is you want to check before you do your computation and to make sure there's nothing wrong with it. All right. So after this unit system be processed, let's look at how we solve it. All right, what we know here, we know the nozzle diameter is 0.5 and the linear flow speed is 50 millimeter per second. Knowing this, we could know the volumes, the volumetric flow rate, right? As I mentioned, we are looking at the watts instead of joule, right? So that means you want to divide the time. That's the energy per unit second. That is watts, right? And that is what you could control for the machine, right? In that case, you want to divide the t for the two side of the equation, and this gives you the watts. All right, so you don't need to worry about it. And what is this? So originally V is the volumes of the material, and T is the time. So V over T, turns out it gives you the volumetric flow rate. So what you have is the diameter of the nozzle and its linear flow rate, flow speed, right? Then you could use this formula to compute the volumetric flow rate. That is the cross-section times the linear speed. And this gives you the cross-section, and this gives you the linear speed. And remember here, see, we need to change this millimeter unit to the centimeter here. And it turns out it gives you a volumetric rate in cubic centimeter per second. And essentially that is here. Then the next will be simpler. You have all this ready, right? And substitute it to this portion. Of course, you have already unified the units, right? Make it consist with each other. And turns out what you have will be the total watts needed in the process. All right. So I will give you like 5 minutes for yourself to solve this, go through this problems. And if you have any questions, just ask. I just want to make you fully understand it. This is very important, and that will give you the basic understanding of how a 3D printing, for how a FDM 3D printer works. All right, go ahead and solve it yourself. So also you want to be aware of this. As I mentioned, so basically when you compute the temperature difference, right? Because the Kelvin is kind of the shift of the Celsius, right? So for both of the temperature, you have this 273 added. And when do the subtraction, this will be canceled. So it turns out it is still the difference between the cells temperatures. So you don't need to worry about the 273 anymore. So just to use this Celsius to compute this difference. That's it. All right. Just to keep this in mind. Okay, I think you have went through this process, this calculation, right? Any questions? No? Good, good. So why we need this?
I have a question.
Oh, yeah, go ahead.
Yeah, so we have that the diameter of the nozzle is 0.5 millimeters.
Yeah.
And then we use for the radio 0.025 centimeters.
Yep.
What is the difference of centimeters and millimeters in that case?
Oh, so basically it's not just you want to divide the 0.5 by 2 because to compute the cross section, let me draw this illustration of nozzle, right? This is the, let's say this is the 0.5, right? In order to compute the area of this cross section, you want to have the radius. So that will be 0.5 over 2. So that will be 0.25 millimeter. And then 0.5 millimeter is 0.025 centimeter. And that is
Okay.
what we use here. So remember,
Okay.
it's here we need the radius instead of diameter. But usually the data given to you is the diameter. So be aware of this. You need to divide this by 2. All right?
All right. Thank you.
So there are little details. So you want to be aware of when you do the computation, and be careful about it. And then you should be fine to do the computation correctly. So the question is why we need this computation. So actually that will determine what kind of heat unit you will be needing for your 3D printer. So usually a 3D printer, FDM, fused deposition modeling printer, is able to print object using different materials. So you want to find out what will be the maximum watts necessary to print among all the different materials. But that amount of watts actually is just the minimum requirement. Why? Because what we come up here so far, like for example, like this, basically that's the ideal case, meaning no energy lost, no heat lost. There's no effect of transition, convection, and radiation. But that's not true for the real machine. It's not possible for the real world. Usually there will be some percentage of heat lost. And in that case, we need to always want to multiply this by a factor which is greater than 1 to make sure the heat unit will work properly to melt the material for the printer. So that is why we need to look at this computation and why it is important. Okay, so I would like to start a little bit introduction about the material aspects as well. So let me find let me open another slide. Yep. So material is also a very important aspect in the fused deposition modeling. And let's look at it. So there are 2 major category of materials in the fused deposition modeling, or the material extrusion, more general speaking. One is the thermoplastic, another one is thermal sets. If you ever taken any material related courses, you should know the major difference between the 2 is for the thermoplastic, you could soften or I mean you could soften and reuse the material repeatedly, right? That's the property of thermoplastic. Although there will be some material property lost for the softening and re-solidification, but you can do it. For the thermoset, you cannot resolve this. So once you melt it and print it, and that's it. There's no way to melt it and solidify it again. So that's the major difference between the 2. We usually use thermoplastic in our printers, and some representative materials are ABS, nylon, polycarbonate, and PLAs. And you have played with PLA here, right? There are some nylon-based ones you could use in your Markforged Onyx machine in the later labs, right? And if we take a look at their structures, molecular structure, of the two different material. And you will find the difference. But before that, let's look, check its a molecular construction of the two different materials. Basically, for the thermoplastic, it could be amorphous or crystalline or simocrystalline or even elastometric. And it supports the melting and remelting multiple times. Basically, with each of the heating cycle, that is melting and solidification, the mechanical property of that thermoplastic will become worse and worse. It degrades, right? So if you check its representation of the material, typically it consists of the carbonate, hydrogen, oxygen, nitrogen, and so on and so forth, right? And basically that's the combination of these, and it repeats them together to build the block. So that is called the Meer units. So these Meer units repeat themselves to build the whole chain of the polymer. And the polymer actually itself means multi-mers, right? Polymer or multi-mers maybe. I don't know. Polymer. So that's why it has such a name, right? So amorphous and crystalline are the two properties for the thermoplastics. If we look at the chains of the polymer, you can tell the difference. So basically, for the amorphous thermoplastic, the chains, the molecular chains, are kind of random. It's like a massive of spaghetti put together, and it's hard to find its structure. And I mean, it's just some randomly placed chains. But for the crystalline, you will find, well, it has a very structured, organized polymer chains like the one showing here. So you can tell it's different, right? So for most of the thermoplastic, they tend to be mostly one or another, but sometimes it's not absolute. These thermoplastic could have some degree of crystalline, and as well as there are some types of semi-crystallines. Basically, these are most crystalline, and it has also some amorphous zones between the crystallines, like the one showing here. So these are the crystalline parts, sorry. And this is the amorphous part of the polymer. So usually it's kind of the combination of the two different structures of polymer chains. And there is another very important polymer, which is the elastomers. And usually for those flexible material, flexible filaments, they are made of such elastomers, like the one Ninja Flex or the Fila Flex. Usually it's called TPUs, right? So this kind of polymer, they elongate when stressed, and it will return to their original shape when the stress is released. So basically, if you look at this, its structure, molecular structures, it's kind of like a set of springs, right? And then you can understand how this could be stretched and released to restore its original shape. And sometimes this is very important properties for printing those elastic objects like the one shown here. Yeah, we also have some of these TPUs in our labs, and you could, for the project, you could think of utilizing them, but this is more difficult to print compared to the normal PLA material, and that requires some special setup other than the normal ones for the PLA printing. Usually it requires slow linear motion of the printing head, as well as a higher printing temperature, right? There are some temperatures, as we mentioned, temperatures, right? There are some temperatures which are very important. So there is the glass transition temperatures. So below this TG glass transition temperature, the polymer is relatively hard and brittle. But above this temperature, this polymer becomes soft and flexible. But this is not for all the thermoplastics, and it applies to only Alformer's thermoplastic. Similarly, there's a crystallization temperature, and if the temperature is above this crystallization temperature, the polymer transits from the unorganized Alformer's polymer to the organized one. I think here is a typo. It should be TC. I will correct it. All right. But not as I mentioned, there are some polymers which are not crystalline, right? In that case, not all the polymer will crystallization. I mean, crystallize, like the polystyrenes. So also another temperature we mentioned previously is the melting temperature. So the melting temperature is that if you heat up the polymer above this melting temperature, at that point, polymer will become a liquid. So this melting temperature is only associated with the crystalline thermoplastic. For this Alformer's thermoplastic, it doesn't actually melt. In that case, it doesn't have this melting temperature, right? These are the things you want to keep in mind. So you might ask, why? How could we know these temperatures? So there is a technology called differential scanning calorimetry. And this is the way you could determine all these temperatures. So it will measure the rate at which the heat flows through a polymer. Usually it provides a device for this computation. And it turns out you will have a curve of the heat flow with respect to the temperature increase. And for the glass transition temperature, what you want to find is the first raise of the flow rate and find its midpoint. And that will be the glass transition temperature. And for this crystalline temperature, crystallization temperature, what you want to know, what you want to find is when this rate drops, and basically that's the bottom of this region, right? And similarly for the melting temperature, that's the top part of the curve. And by plotting this kind of curve and look at the curve, you could find out all these temperatures. And that is all done by this DSC method. So in the material extrusion or fused deposition modeling, the thermoplastic filament is heated above its glass transition temperature for the amorphous thermoplastic. But for those semi or crystalline or semi-crystalline thermoplastic, you want to heat the temperature up the melting temperature, such that you could have the liquid flow, which could be pushed through the nozzle. And there are some typical materials as I mentioned, right? The PLA, ABS, TPU, polycarbonate, and Ultratem. Or there are some nylon or some PETG material, or some combinations of these plastic and other material like the chopped carbon or glass fiber with nylon. So actually this one is the one we utilized for the Onyx machine, the Markforged Onyx machine, and you will see what it gives you as a combination composite material, and actually it gives you a better material property, mechanical property, compared to the other plastic-based material. So for the printing process, there could be some other aspects as well. For example, you could add some so-called the plasticizers, and that will, by adding this, that would lower the glass transition temperature and increase the flexibility of the polymer. So it's kind of adding oil to the spaghetti that helps the polymer chain slide more freely, and that gives you a little flexibility as well. Also, you want to prevent the flames, because there's a heating up material process and it exposed in the air. So you don't want to have the flames. So that's why this flame retardants will be necessary to be added in the polymers. Sometimes you want to have the stabilizers as well. For example, there are some additive manufacturing process some products printed using additive, and its working environment has the UV lights or sunlights, right? And you want to have the product to bear longer time with the UV light exposure. In that case, the stabilizers are necessary to be added to change the material property a little bit in order to satisfy the need, right? Or some prevention of the oxidations, and that will be another very frequently seen cases, because the part printed or the object printed in the additive, if you put it in the working environment, let's say in a factory, there will be other chemical particles over there, and there could be some oxidation during this process, during the usage of the parts. And these antioxidants are necessary to be added to be as stabilizers during the printing process. So just basically, this is nothing new, actually. If you take other plastic-based process, take a look at them, it's quite similar. There's nothing new for additive, right? So another problems is the moistures. So the plastic can absorb moisture if it get exposed in the airs, right? But that's not a good thing for the printing process. So just to think about if your 3D if the filament used in your 3D printing have moisture there, if it's moist, what's gonna happen? Any thoughts on it?
When you heat it up, you could get like void sections.
Yeah, exactly. So basically, you will have you will get the water particles boiled, right? And that will create void or bubbles. I mean, to be more precise, it's bubbles in your prints, and that is definitely I mean undesired. You will have gaps or void in your prints. So that's why you want to always to dry your prints. I mean, dry your filament if it get moist there. And basically, you could put it into the oven and heat it for several hours. And also, you want to be aware of the glass transition temperature, and also that will affect the temperature you set up for the drying. Definitely, you do not want to set a temperature for drying which is above the glass transition temperature, because that will melt your filament and mess up your filament. So be aware of this and make sure you do not set a too high temperature here, right? Another way to prevent this moisture absorption, that is, well, how about we have a case, a box, to keep the dry filament and make sure it will not be exposed to the moistures. So that's another way, also a typical way to deal with this. If you look at the Onyx, the Markforged Onyx machine, actually it has a box to keep its material, because the material they use here is the nylon plus the carbon fiber or glass fiber. And nylon is the material which will easily get the moisture absorbed. And that's why we always want to keep it in a box. All right. So if you check the material properties for the printing material for the material you want to print using a printer, basically there are some representative material properties like the one for ABS. You will have all different material properties parameters from the manual of your printer, the manual of the from the manufacturer of the material, and be aware of them before you use it. And again, this shows you a combination. Basically, we put everything together and let you know the material property. So also there are other properties of importance. For example, the heat deflection temperature. So as you know, the polymer or the plastic material will become softened when heated up. So this heat deflection temperature gives you some idea, that is how much it will be deformed when get heated, and what is the temperature. So what they do is they have this 3-point bending test with a preset pressure. So this pressure is fixed, is given, and then you just heat up. This is actually the experiment setup. And in this tank, basically at the bottom, that's the heater. So the heater will hit this sample part, and there will be a pressure applied here. So this is one contact point, and there are 2 contact points to support this sample plate. And with the temperature increase, there will be the deflection or deformation of the part. And because this pressure is the given, is unified, and you will have the temperature recorded for the heat diffusion deflection happens. So that's how you determine the heat deflection temperature, as shown here as well, right? Another important property or parameter for the plastic material is the coefficient of thermal expansion. And that increases the material length per degree change in temperature per unit length. So that gives you a ratio of the material length change with the temperature change. So here show you how it could be computed, right? So as you can see here, there will be a expansion when the temperature get increased. So one last thing is, can we kind of improve the thermal, the material properties for the plastic prints? So actually there's a process, post-processing, called thermal annealing. So that is you heat, after you 3D print the part, you want to heat up the part in an oven to relieve the shrinkage stress. And also to recrystallize the material. By doing so, you have a better material properties. That is so-called thermal annulings. It's similar to those annulings for the metal materials. As you can see here, after the recrystallization, you will have a much better structure for the material. Actually, there is a test conducted to this Markforged onyx material. Basically, you will have a increased ultimate tensile stress from 29 something to almost 40, and the yield strength increased from 29 from almost 40, and the modulus or stiffness modulus, Young's modulus, which is related to the stiffness, increased from 740 something to 1420 something. Also, the impact energy at break decreased from 10.7 to 5.4. Basically it will become more brittle in that case, right? So previously, the impact energy at the break is larger, and after this annealing process, it become lower, right? That's the only thing you lost. All these are good, but this one, it make your part more brittle. But that's it's kind of, you always have a balance. You always to choose whether you want to have a stiff material or you want to have a material with more hardness, right? So that's thermal annealing. I think that's all for today's lecture. And I will post both of the lecture notes online, and I will post the first homework also as well. And you have 1 week to complete it. All right? Any question?
Oh,
No? Okay, good, good. Okay, thank you for your attention, and let's keep in touch. And hopefully see you next week. All right?
all right. Thank you, Professor.
Yep.
Thank you.
Yep. Okay, bye, guys.
Thanks. Have a great week.
Mhm.